Okay. Hello everyone. I'm very happy to be here for this invitation to give my talk. And I'm Sheng Hsiung. Okay, so I'm from Chung Yuan Christian University of Taiwan, and the title of my talk is realization of 20% inverted Proposed solar cell. Okay, so I think solar cell is a hot topic. And now the highest efficiency is about 25%. And this is the progress. And we can see here the solar cell performance of Proboscite solar cell. Okay, it is higher than the CIGS solar cell, OPV solar cell, quantum dot solar cell, and the bicentennial solar cell. And the efficiency of Proboscite solar cell is close to the performance of silicon solar cell. And when we use the Proboscite silicon tandem solar cell, the efficiency can be higher than the gallium arsenide solar cell. Okay. And let me try to introduce what is the Proboscite crystal. This is organic, inorganic Proboscite crystal. It contains organic material and inorganic material. Here the A side is the organic or inorganic cations. It can be inorganic cations also, but when we use the organic cation in this material, the opto performance will be better. And B is the metal, S is the halide anions. The material is optical band gap is from 1.5 electron volt to 3 electron volt. So this material is suitable for the optoelectronic devices. And this material, it has these superior optoelectronic properties. The absorption coefficient is high, the refractive index is relatively low, and the epsilon binding energy is small. So it means that it is easy to form the free carrier in the Proboscite crystal. And it has the long epsilon lifetime, the long epsilon diffusion length. So it's easy to form the free carrier. And this material, it also has the shallow defects. Okay, so it's not easy to has the potential loss. Okay, and this picture is proposed by Professor Walsh. It means that the cation can be considered as these dipoles. So the electron flow and the hole flow can be separated spatially. So the electron and the hole, they will not be combined. They will not be combined easily. So the field factor is high in solar cell. Okay, so I think this is the main concept of Proboscite solar cell. And this concept was demonstrated by Professor Cho's group. Okay, they use the FM-based technique to see the energy transport. Okay, energy transport. This is dark condition. This is illuminated condition. So under the illuminated condition, the electron and the hole flows, they are spatially separated. Okay, so Professor Cho's group just tried to demonstrate this idea. And we know the solar cell material can absorb the light. Okay, so it must have a broadband light absorption. And in this spectrum, okay, it contains two Lorentz oscillator and one continuous band absorption. Okay, so that's the main reason why Proboscite crystal can effectively absorb some light. And Proboscite crystal thin film, it also can be easily fabricated by using solution process. Okay, so we can just put MAI, PBI2 into these solvents. Then we can easily get the Proboscite thin film. We can use this method to fabricate Proboscite thin film. Okay. However, this method, they suffer the same problems. When we try to increase the grain size, the surface roughness will be larger. Okay, so if you want to get a smooth surface, the grain will be small. So there's a trade-off between the grain size and the surface roughness because we are trying to do the thin film based devices. And from this page, you can know about 60% of sunlight can be absorbed by perovskite crystal film. And according to the voltage laws, the highest PCE of a single junction perovskite solar cell is about 30%. Now, the highest efficiency is 25%. So it means that it is possible to increase the efficiency to 30%. Okay, the perovskite solar cell can be classified as the two types. One is a regular type, another one is inverted type. This one, the highest efficiency is higher than this one. Okay, and in the regular type perovskite structure, they use the TiO2, okay, N-type material in the bottom layer. However, the drawback is the sintering temperature of TiO2 is very high. So this structure usually cannot be used for plastic substrate. And when we use the inverted type structure, usually conductive polymer, okay, some polymer material, they are used in the bottom layer. However, this material, it can be dissolved by water. So the device stability usually is low. And this is the first regular type of perovskite solar cell. Professor Miyasaka proposed this solar cell, and the efficiency is about 3.8%. This study was published by JES. And this is the first inverted type of perovskite solar cell. It was published by Professor Guo. Okay, they published this paper in Advanced Material. Efficiency is about 3.9%. Here, they also use the PSS as the Hall transport layer, use the PCBM as the electron transport layer. This layer is the light absorbing layer. PCB is a electron modification layer. So they just use this structure to realize the perovskite solar cell. If you want to know how to increase the power conversion efficiency of perovskite solar cell, you can try to understand the energy diagram. Okay, this is a light absorber. When the light absorb electron, when the light was absorbed by perovskite, it can generate electron in a whole pair. Then electron can be collected by ETL, or can be collected by HTL to form the free carrier. Okay, so we can use this equation to calculate the power conversion efficiency. Okay, so the voltage loss become very important. It means that we need to try to minimize the voltage loss. Okay. Okay, so we also need to know how to fabricate the high performance perovskite thin film. This is the first method they use. They use MAI plus PBI2. This is a one-step solution process. And they just add the HI as the additive. Then the different concentration of HI can change the morphology a lot. Okay, so this is the first method. And in the ratio, they also can use a two-step interdiffusion process. They will fabricate PBI2 first, then fabricate MAI, and through the interdiffusion process, it can form the perovskite thin film. And the main drawback is that there is a long interdiffusion time. The optimal time is about 2 hours. And we also can use the washing enhanced manipulation process. During this spin coating process, the anti-solvent, okay, can be used, okay, then to form a good surface morphology, then achieve a high efficiency. Here, the anti-solvent is taurine. In the same month, other research group, they also propose such method. They use chlorobenzene. Okay, they use chlorobenzene during the spin coating process. They also can achieve a high efficiency. Okay, so I just try to learn how to fabricate the high performance perovskite solar cell. So we just follow this structure, inverted type structure, P-type material, light absorbing material, N-type material. So the three layers, they can be fabricated by using solution process. Then the silver must be fabricated by using thermal evaporation method. Okay, but we know ITO, it is a hydrophobic material. PSS is a hydrophilic material. PCBM is a hydrophobic material, and the Proboscial is a crystal. So it must contain a lot of interfacial problems. Okay, so in the following year, in recent year, we just try to resolve this problem. Okay, this is my first Proboscite solar cell paper. We use the taurine. Okay, we use the taurine also, or try to understand what happens when we use taurine as the anti-solvent. So when the taurine is used, it can form the closely packed smooth thin film. Okay, then you also get the isotropic X-ray diffraction pattern. Okay, you can see here the IB curve is improved. So this one, the efficiency is about 10 or 11%. And we also try to study the concentration effects, the concentration of Proboscite precursor solution. So change the concentration from low concentration to high concentration. Then we get this optimal concentration is about 1.45 mole. Okay, so you can see here, there is a trade-off between the surface roughness, and the grain size. And we also try to understand the boiling point of anti-solvent. What's the effect from this parameter? So we change the boiling point of anti-solvent from this degree to this degree. So when we increase the boiling point, you can see here the JC can be increased. However, the VOC is decreased also. But overall, the efficiency can be increased by using a higher boiling point anti-solvent. The main reason is that when we increase the boiling point, the surface roughness can be kept. However, we can slightly increase the grain size. Okay, and we also try to study the anti-solvent volume effect. So when we increase the anti-solvent volume from 0.1 milliliter to 0.7 milliliter, the surface morphology also changed a lot. And we also can use the transmittance spectrum to evaluate the refractive index. So you can see here, when we increase the IB volume, the refractive index increased. So it just tells us the film density is increased also. And we also try to study the dropping time of anti-solvent effect. So the optimal dropping time is in 13 seconds. Okay, so you can see here the morphology change a lot also. And we also try to study the impurity effect. And we can use the different dropping time, then try to minimize the current hysteresis effect. Okay, we know the defect, when we try to add some defect in the Proboscite material, it will give us some photocurrent hysteresis effect in the JC. So we can try to change the dropping time and also add 10% of DCM. Then the photocurrent hysteresis effect can be reduced. Okay. And what is the origin of photocurrent hysteresis? Okay, it is from the halide migration. So in Proboscite material, if we only use MAPPI3, the ion migration energy of iodide is lower than the MA. So usually the iodide can migrate in the Proboscite crystal. But if we add some BR, okay, in the Proboscite crystal material, then the ion migration energy will be increased. So it means that the additional BR can reduce the halide migration, then reduce the photocurrent hysteresis. Okay, in this study, we also try to passivate the defect by using the capping layer. The capping layer is a small molecular, N-type small molecule. It forms the PCBM thin film. We use the SRD and the RAMA to see the defect preservation effect. So after the capping layer of PCBM, the defect can be preserved. So here are the evidence. And the preservation also can be observed by the peer quenching and by the normalized peer spectrum. So we can see here the defect was preserved by using PCBM. And we also try to study the interfacial concept problem. So when we increase the surface roughness, the shape can be reduced. Okay, so the surface roughness is also important. And we also can see here, without the PCBM, the SRD intensity changes a lot. So it means that the contact is very important because the contact can passive the defect. The contact also can change the residue trace of Proboscial same thing. And here we just try to resolve all of these problems. So here we get two situations. In the first situation, situation one, there is an electrical barrier at the PCBM MA PBI3 interface due to the existence of interfacial MA ions, which can be used to explain the edge shape, okay, of the curve. And in the situation two, the PCBM, okay, this situation can effective contact with the MA PBI3 thin film when the interfacial MA ion are removed. Okay, so this case, just let us guess the PCB IPS spin coating process is not only used as the electron modification layer. There is a diffusion process, diffusion of PCB and IPA. Okay, this is our first demonstration. We use the PCB IPA diffusion process. Then you can see here the shunt resistance become beta, series resistance become smaller, so we can improve the field factor also. And in literature, they just claimed the PCB can form a layer, but we don't think so. So we try to understand it. So when we use the PCB, okay, and the IPA to remove something and passivate something, some defect, so we can improve the carrier transport in PCBM, but we also can passive the surface defect. So this is the experimental result. So when we use the IPA, ethanol, methanol, and without any treatment, you can see here with the time, the material, Proboscial material, will change the color because the Proboscite, okay, Proboscite crystal will dissolve by this solvent. Okay, so this is the demonstration. The Proboscite can be dissolved after the diffusion process through the PCBM thin film. And here we only use the solvent. Okay, then after the reaction time 30 seconds, then the edge shape can be resolved. And when we add the PCB into the IPA, you can see here the photovoltaic performance will largely increased. And from the Assoc spectrum, from the SRD spectrum, from the RAMA spectrum, okay, we prove that the PCBM can be modified. The interfacial contact can be modified by this evidence. Okay, so 1 year ago, we just achieved this value about 40%. So we just try to think how to increase the efficiency to 20%. So the goal is reducing the defect and increasing the crystallinity. Okay, and we also try to modify the PDA PSA thin film. So there are two papers. So we try to do something, but we did not exactly increase the efficiency to 20%. Okay, this is the some study about PDA PSA thin film. Okay, because we want to increase the VOC and increase the field factor, so we need to know the defect density distribution in the Proboscial thin film. Professor Sheng Hsiung Chang, they just claimed the defect, they are mainly distributed in the bottom layer and the top layer. So we think we need to change the substrate. So we try to read some paper. Okay, so they use nickel oxide, organic material, okay, oxide-based material, polymer, oxide-based material and the PDOT. Okay, so all of these they can be used to achieve the higher efficiency. Okay, we also use the PDOT PSS, but we cannot reach this. And in literature, only 2 papers they can reach this efficiency. So we want to use the solution process also. So we select this P3CT based HTL. So this is our first reference paper. We follow the same fabrication method. They can achieve about 16% efficiency. Okay, you can see here, when the PDOT PSS is replaced by P3CT sodium, the VOC can be largely increased. The field factor also can be increased. And this paper, they try to use the different P3CT based material. Okay, so when they use RB, then the efficiency can be increased to 20.5%. And then in our study, we just try to use the P3CT sodium thin film. But in this study, we try to use the different filtering process. So we use one step of single filtering process and double filtering process. Then the efficiency can be increased to almost 19%. Our analysis shows that the filtering process can remove the large aggregates and also remove some hydrophobic P3CT because we want to form some hydrophilic P3CT on top of the ITO surface. And when we use the double filtering process, you can see here the PL spectrum shows that the contact is better because it has the larger PL quenching effect. Okay, and the FM imaging also tells us the lower eye. Okay, the lower eye indicates the beta interfacial contact. Okay, at the P3CT sodium ITO interface. This contact is very important. And we also use the RAMA spectrum to see the crystal structure of Proboscite thin film. So in the double filtering process, the Raman signal from the PBI and the MA liberation, their intensity is higher. So the higher intensity just tells us the crystallinity of Proboscite thin film fabricated by using double filtering process is better. Okay, so it also tells us the interfacial contact at the MAPBI3 and the P3CT sodium interface can be improved by using the double filtering process. Okay, this is our final result. We can increase the device efficiency to 20%, and the field factor is very high, 80%. Okay, so here is my conclusion. The rules of PCB IPA penetration effect are investigated for the first time. A high power conversion efficiency of 20% can be achieved by optimizing the fabrication parameters of inverted type Proboscite solar cell. The most important one is the formation mechanism of hydrophilic Proboscite thin film on top of the hydrophobic P3CT sodium thin film is not completely understood. So we are trying to understand this contact. We think if we can improve the contact, then the efficiency can be increased further, maybe 25%, maybe 30%, it is possible. Okay, so thank you for your attention. I'm from Taiwan. This is my lab, ODSOS lab in CYCU. Okay, thank you.